Yes, ma'am.
Okay. So now we're going to discuss about routing. So in the last class we have completed a configuration of routing. Okay, what should be the router? What are the components are available? And what about the input port, output port, switching fabrics, and all those things. In router perspective, there are two basic operations. One is forwarding, another one is routing. Okay, forwarding and routing. Okay, so forwarding, whenever it gets a packet from any one of the input ports, should be forwarded to any one of the output ports. Okay, that process is known as forwarding. But to make that a decision, which output port to be used, okay, so for that decision, it should check the hash forwarding table. Okay, so each and every router is associated with a forwarding table. Okay, just to perform a lookup on the forwarding table to make the forwarding decision. Okay, but here the question is how that forwarding table to be constructed by the router. Okay, so what is the idea behind the construction of that forwarding table? Because a forwarding table that provides a least cost route to reach the destination. Okay, so the idea behind that forwarding table or the mechanism behind the forwarding table is a routing algorithm. Okay, routing algorithm playing a role. Once the routing algorithm is implemented, automatically each and every router will have appropriate forwarding table to make the appropriate choice. Okay, so we're going to talk about routing, and today in specific, we're going to talk about one important routing protocol, or one widely used routing protocol called link state routing. Okay, but before that, let me give you some info about routing, because routing is a strategy, routing is a mechanism inspired by mathematics called graph theory. Okay, so first of all, we have to understand how this routing problem to be defined in graph theory. Okay, so then we move on to link state routing. Okay, so the routing perspective, if you take any network topology, definitely the router to be associated, each and every host to be associated with one of the router. Okay, so for example, let me take a small picture here. Host A, okay, so let me take a simple topology here. So this is a sub network. Okay, sub network made up of routers. Okay, we have five routers here. So this is actually sub network. Sub network is just a part of the network core. It won't generate any data. It simply forward the data. Okay, so for example, in this sub network, okay, the host, sender, or destination, or all these elements are known as end system. Okay, end system or host. Okay, so the host to be associated with any one of the router. Okay, but let me take one simple example here. This is actually a host A. Okay, so host A, sender, and this is host B, a receiver. Okay, end system, host A and host B. Okay, so to reach this destination, let it be this is sender, okay, and this is a destination host. Okay, so the end system, to reach this destination end system, definitely it should be connected with this network. Okay, so the host A to be connected with any one of the router. Let me take this is attached with this router, and this node attached with this router. Okay, so for example, if the packets are transmitted from the sender to receiver, okay, the direction of the packet flow is in this direction, from sender to receiver. Okay, so sender to receiver, this router, okay, is named as source router. Okay, or otherwise it is also known as edge router. Okay, so source router, we can call it as source router. In the ATM network and some network, it also known as edge router. Okay, edge, entry level router. Similarly, this router is also named as destination router. Okay, so destination router, again it is also known as edge router. In some cases, this is known as egress switch, and this is ingress switch, entry level switch, exit level switch. Okay, so there are different names are available. Okay, so this is the entry point for the forwarding process, and this is the exit point for the forwarding process, because this is normally the host to be attached with any one of the router. Okay, so now here this is the entry point for the entire process of transmission, and this is the exit point for the entire transmission of the process. Okay, what we need to do here is, there is a need to find out the best path from this entry router to exit router. Okay, that is what ultimately our requirement. Okay, so for entry to exit, we need to find out a best path. Okay, what do you mean by best path? Best path means normally it is least cost path, least cost route. Okay, least cost route. Okay, what about the cost? The cost sometimes it may be the delay in each and every link. Okay, so we need to reach the destination with minimal delay. So here the cost is nothing but the delay metric. Okay, so sometimes that the link may be the link or indexed by traffic or load. Okay, load in that link. Okay, so in that case you have to find out the link with the lowest load. Okay, so then only the packet can be forwarded effectively. So in that case the cost may be the load. Okay, so sometimes if all the links are homogeneous link, okay, that is not possible, that is actually utopian, that is imaginary. Each and every links are different capacity and different type of multiplex link. Okay, but assume if the links are homogeneous link, then the least cost route is nothing but a route with minimal link. Okay, in that case the cost is nothing but hops. Okay, so minimum number of hops, otherwise minimum delay or minimum load. Okay, so the cost factor can be anything, but whatever it may be, we need to find out the minimal element. Okay, so objective here is we need to find out least cost route, that is known as best route. Okay, not optimum route, best route. Okay, so we need to find out the best route from source to destination. Okay, so in this case, if each and every router, to find out the best route, now let's see this particular subnetwork. You needs to find out the best route to reach is it not host B. Okay, because routers knows other routers, not the end system. Okay, so this router should know the least cost route to reach is it. Okay, so if it is so, what is the requirement here? So the router should know the information about the in-between links as well as all other in-between routers. Okay, so the routers should maintain some global information to make this a decision. Okay, so that one is one type of routing strategy. Okay, that is based on global state information. Okay, I will write it out. That is one type of strategy based on global state information. Global state information. That means each and every router knows about all other router in the subnetwork, the capacity of the link in each and every other router. Okay, so that global state information to be used by the router to make the decision. Okay, what is the decision? Finding out the least cost route. Okay, that is one thing. Another one is local routing, global routing versus local. So in the global routing, the problem is that if you take any subnetwork, it has billions of routers connected with the different links. Okay, so acquiring information about all other router in the subnetwork is a tedious process. And one more point here is there is a possibility of single point of failure also. Okay, so the global routers requires, because all the routers are commodity hardware with a limited memory and limited computing power. Okay, so if there are billions of routers collecting all the information about all those router and processing, applying some centralized algorithm to decide the least cost route seems to be tedious. Okay, so that we have alternative strategy called local. Okay, so in that local, each and every router acquires information about only its direct neighbor. That's it. You knows about its neighbor B and X. Okay, it should know the least cost route to reach its neighbor alone. Okay, so similarly, each and every router knows about its neighbor. Okay, so based on that neighboring information, the router decides least cost route to reach other non-neighbor routers. Okay, so that is known as local. Okay, so global versus local is one way of differentiating routing algorithm. Another way of classifying the routing algorithm is nothing but static versus dynamic. Okay, or otherwise it is also known as adaptive versus non-adaptive. Okay, what is static? So once the topological informations are collected, the router just decides the least cost route, okay, and never change the route later. Okay, that type of routing is known as static routing. But in a normal scenario, network scenario, or TCP/IP point of view, static routing is not suitable because links are highly adaptive. Links are multiplexed with different channels. The load in the links are highly dynamic, and the router may also get down at any particular point of time. If it get down at particular point of time, then we need to find out alternative route. Okay, so the entire topology itself is dynamic, highly dynamic. Okay, because if you take a mobile network, mobile ad hoc network, each and every mobile nodes are nodes. Okay, each and every mobile nodes are forwarding device. Okay, so in that mobile node, the particular router or forwarding node may enter into the coverage area or may exit into the coverage area. That may happen very frequently. So we need a different type of routing algorithm to adapt the changes in the topology. That algorithm is dynamic. Okay. Another name for static routing is non-adaptive. Okay, it won't adapt the changes in the topological structure. But dynamic routing is known as adaptive routing. That means it adapts the changes in the topological structure. Okay. So actually, global routing or local routing. Local routing, and otherwise I can also call it as decentralized routing. Okay, global routing. Another name for global routing is centralized routing. Okay, another name for local routing is decentralized routing. Okay, so similarly, the static versus dynamic. But in today's scenario, one more classification is just emerging because of the content provider. Because normally the trend is based on the winners. Okay, so today's winners are Facebook, YouTube. Okay, so they decide another type of routing called load sensitive routing and load insensitive routing. That is another classification. Okay, so load sensitive routing and versus load insensitive routing. That means the routing, the least cost route is decided based on the current load in the path. Okay, so whenever the load increases in the particular link, then automatically the router should select alternative path. Okay, so that is nothing but a load sensitive router. Okay, so if the particular destination router is something related to the content service provider, content distribution center like YouTube, this one particular route may be heavily loaded route. Okay, so you have to select the alternative route by considering the load factor here. So load sensitive routing, and another type of routing is known as load insensitive routing. Okay, initially, if you take a link state routing or distance vector routing, those traditional routing algorithms are load insensitive routing. But today's emerging trend is load sensitive routing because of the content which are distributed over the network. Okay, so these are the different classification related to routing. But before getting into the routing strategy, I said that the routing algorithm is defined in terms of graph theory problem. Okay, so let us just map with the graph theory. If you take graph theory concepts, graph consists of two things. Okay, edges and nodes. Okay, if you take any graph can be represented like this. Okay, represented by using just simple notation. Set of edges, okay, as well as vertices. Okay, if we take simple notation, if you take a graph, it consists of edges and vertices. Okay, set of edges and vertices. And here the vertices are nothing but routers. Okay, so vertex is nothing but a router, a forwarding device. Okay, router or switch. Edge is nothing but a link, transmission link. Actually, the graph is a weighted graph. Okay, why weighted graph? Because each and every link is assigned with a value. Okay, that value is nothing but a cost of the link. Okay, but what is that cost? Is it a bandwidth or is it a load? That depends upon the least cost route. Okay, if you want to compute least cost route with a cost is a delay metric, then this needs to be weighted with a delay. Okay, you have to find out the minimal delay link. Similarly, if it is a load sensitive routing, these links are assigned weighted with the value load. current load at particular point of time, what is the load, okay, because these links, the values not fixed, okay, so the values are highly dynamic at particular point of time, that is at time t0, the weight from u to v may be 2, at t0 plus some seconds, the weight may be something different, okay, highly adaptive, so the weights are nothing but a cast, okay, so that I can represent in terms of graph theory, set of edges and vertices. Edge is represented by a pair of vertices. Okay, edge is represented by a simple pair of vertices. For example, here if you take a particular edge, u comma v, this is actually one particular edge. Okay, so each and every edge is represented by a pair of vertices. Okay, so for example, here u comma v is one edge. Okay, and its adjacent edge is known as neighbor here. Okay, it's adjacent edge. Okay, for v, its adjacent edge is nothing but u comma v, its adjacent edge is v comma w. Okay, as well as v comma x and u comma x. Okay, adjacent edges are known as neighbors. Okay, neighboring vertices and neighboring edges. Okay, so we can easily map this particular topological structure, wired topology or wireless topology, whatever it may be, we can map with a graph theory concept. Okay, we can directly apply the graph theory algorithms to find out least cost route. Okay, so the nodes are nothing but vertices and edges are represented, transmission links are represented by edges which connects two vertices. For example, if there is no route, for example, no link from v to y, there is no link. Okay, so the way the cost to reach y is nothing but infinity. Okay, that is there is no direct link. If there is no direct link, then we can assume that there is no route to reach y directly. If there is no route to reach y directly, then that link to be assigned with a value infinity. Okay, so this is a simple mapping of subnetwork into weighted graph. Okay, but the weighted graph, directed graph, undirected graphs are available. But if you take a link, okay, this is actually a full normally it's a full duplex link. Okay, so we assume that the transmission rate or delay from u to w is same as w to v. Okay, we assume that if it is delay from u to w delay, w to v delay seems to be assumed to be same. Okay, if it is so, then this will be undirected graph. Okay, that means v to w cost is 3, w to v cost is also 3. It's undirected graph. Okay, but it may not be true always because the multiplex is a link. And if you take satellite communication, downlink frequency is different, uplink frequency is different, uploading capacity is different, downloading capacity is different. Okay, in that case, you have to use weighted graph. Okay, sorry, directed graph. Directed graph, each and every link to be assigned with a different weight. U to W cost is based on uploading rate of V. W to V cost is based on uploading rate of W or downloading rate of V. Okay, so that the graph can be either directed graph or undirected graph. But initially, to understand routing protocol, routing procedure, we assume that the graph is directed. The cost from U to W is exactly same as the cost from W to V. So we have simple assumption like that. But if you take load sensitive routing, definitely this will vary. Okay, because from load from W to V, something different from V to W. Because W is a router not only connected with V, W is a router connected with U also, is it also. Okay, V is a router connected with X and U. Okay, it will get the traffic and load from U and V, X. Similarly, W will get the traffic from X, Y, Z. Okay, so the load in W may not be equal to the load and at V. Okay, so you can represent those things by using directed graph, weighted directed graph. Okay, so the links, we are going to talk about the routing procedure. First, global routing or centralized routing. Link state routing is an example for centralized routing. Okay, decentralized routing or local routing or decentralized routing. Distance vector routing is an example for decentralized routing. Okay, today we are going to concentrate on global routing, that is link state routing. Okay, global state information to be maintained by each and every router. Each and every router first collect the information about all other routers, then select find out least cost route. Based on that route, it will construct the forwarding table. Okay, so we'll do how these routers are constructed. How does the routers define the forwarding table after the completion of the routing algorithm. Okay, so discuss that global routing algorithm. Example, link state routing. Okay, in TCP/IP point of view, the link state routing is named as OSPF, that is Open Shortest Path First Route. Okay, so let's see that routing, link state routing, one of the successful and the most important routing strategy, link state routing. Okay, and let me take new page here. Okay, I need this diagram also. Okay, fine. So we're going to talk about link state routing. Okay, so link state routing is based on global state information. Okay, each and every router should maintain a global state information. Here is in routing perspective, state information is nothing but data points. Okay, that means the capacity of each and every link and what are the in between routers and neighborhood router. That is, you should know, you should know the existence of all other router. That is X, Y, Z, V and W, as well as the task to reach each and every other router. Okay, the link capacity. Each and every router should know the entire topology. Okay, that is global state information. Okay, and this link state routing in TCP/IP point of view, this is named as Open Shortest Path. This is implemented. Link state routing is implemented in shortest path first. Okay, so open shortest path first is the implementation of link state routing in TCP/IP. Okay, so how this particular link state routing is implemented in OSPF we'll discuss later. So just for understanding, OSPF is a implementation of link state routing which is widely accepted in TCP/IP protocol suites. Okay. And in link state routing, the principle, the mathematics behind this is nothing but our shortest path algorithm. Okay, so a well-known graph theory based shortest path algorithm. Okay, what is that? What is that? No, Dijkstra's shortest path algorithm. Okay, actually, this is not only Dijkstra's shortest path algorithm; it's also based on combination of Prim's and Kruskal algorithm also. Okay, because we have to construct the spanning tree. Okay, I'm not going to talk about spanning tree and all those things in the detailed manner because all those things you know already. It's not a part of the NETER syllabus also, but I'm going to touch this. This algorithm is based on shortest path, single source shortest path algorithm, and like a spanning tree based algorithm like Kruskal algorithm, Prim's algorithm, and all those things are inspired for the design of this link state routing. Okay, so let's say here this is a topology given. What we have to do ultimately after implementing routing algorithm, see for just to take it out the router U. Okay, for this particular router, I need to construct a forwarding table. Okay, so forwarding ultimate requirement for this routing is I have to construct a forwarding table at particular router U. Similarly, the forwarding table to be constructed at U, V, W, X, Y, Z and so on. Okay, but I am going to concentrate on the way in which the forwarding table to be constructed at the first router U. Okay, so to construct the forwarding table, first of all, U router should acquire some information about all other router, and so based on that information, it should construct the forwarding table. In this routing strategy, we have one special ICMP packet, Internet Control Message packet. Okay, so let's write it out. Internet Control Message. Okay, so that carries only control data. Okay, it won't carry any payload. Okay, because here the routing information to be exchanged between each and every router. Okay, routing information is not a payload. Okay, it's not a data. Okay, routing information is nothing but a metadata, a control data. Okay, so those information should be inside the control message, internet control message, ICMP packet. ICMP packets are high privileged packet compared to IPv4 or IPv6 data packets. Okay, so in this case, internet control message protocol executed, and the first thing I said this is a global state information. Okay, so what's a way to acquire? How does the router acquires this global state information? Okay, that is based on just advertisement. Just each and every router just advertise itself. That means existence of the router. I said router is a self-configurable node. Once the router is plugged, automatically it configure itself. Okay, so router, each and every router should advertise itself, okay, by sending a special echo packet called link state packets. Link state packets. So link state packet is a type of ICMP packet, internet control message packet. That link state packet just includes its identity, its IP address of the router, as well as the neighborhood link cast. Okay, so for example, you should advertise itself. How? Its IP address, and it should advertise that it has three links: one to reach u, one to reach x, one to reach w. Okay, so the advertisement to be made by B is nothing but three edges: u to b to w with a cost 3, b to x with a cost 2, p to u with a cost 2. Okay, that should be advertised, that should be given, that information to be given to all other node. Okay, if anything to be given to all other nodes, we have to do one type of element called, sorry, one strategy called broadcasting. Okay, so broadcasting is again as a part of routing. Broadcasting is nothing but sending information to all other router in the subnetwork. Okay, so the link state packet is a broadcasting packet. For broadcasting packet, okay, see, one particular person wants to communicate, X wants to communicate to Y. Okay, so if X wants to communicate to Y, then X can say that, hello Y, I have information for you. Okay, so X should know Y's address, then only the communication is possible. But X wants to communicate something to all. Okay, no, then no need to know about the address of all, just X can shout like anything. Okay, so in this case, the broadcasting means we need not know its existence or IP address of all other routers. Simply can send the packet to each and every outlink. Automatically, the packet will be forwarded to all other router. Broadcasting is a different type of routing strategy. It's based on the concept called flooding and other type. I'll talk about that later. But simple idea here is the link state packet, that is state information about each and every router to be advertised by itself. How? By sending the broadcasting message. Okay, the message to be transmitted to each and every outlet. And see, for B, since it's a broadcast link state packet to W, it's link state packet to W. W, after receiving the link state packet of B, it just forward the packet to all its link, all its outlink. Okay, so automatically you will also knows about that. Y will also knows about that. Okay. So that is actually a broadcasting. So each and every router should advertise itself, its topological information, by simply broadcasting the link state packet. Link state like packet contains link cast and its own identity, and that should be transmitted to all outlink by using a broadcasting. So that initially, before implementing or before starting this link state routing, each and every router should advertise itself. Okay, so each and every router now it has a link state packet from all other router. That means you has the link state packet from B, you has the link state packet which is from X, and you also should have the link state packet from Y, and you should have the link state packet W also. So you should know each and every other router's state information. Only after that we can start implementing this, because it is a global routing protocol and centralized routing protocol. Okay, global centralized routing protocol. Okay, let's start this. Okay, so now let's make things here. Some terminologies, just I'm going to introduce some terminology here. Some graph theory based notations I'm going to use. Let's see, we are going to find out a path. We are going to construct the forwarding table. This is what our ultimate aim. Okay, U is a starting node. So some notations, let me take the first notations, terminology, D of V. Okay, and another one P of V, and I have n number of nodes, okay, and another notation n prime. Okay, so what are these? So this D of V is nothing but least cost root. Okay, it's cost of the least cost path. Okay, cost of the least cost path from source node. Here the source node is nothing but U. Okay, so source node, I have taken the source node here as U. From node U to node V. Okay, any node V. Least cost route. Okay, then P is nothing but whenever you move the packet from one node to another node, see you need to forward the packet to its neighbor one. Okay, so after receiving the packet from the U, we need to forward the packet to its neighbor only. So every time you need not worry about the entire path. Okay, you need not worry about entire path to reach exit. Okay, only it should know in which particular link the packet to be forwarded. That's it. Okay, so that P of V is nothing but a previous node, just a predecessor node, or the previous vertex or previous node in the current least cost route. Okay, previous node in the current least cost route. Previous node in the least cost path. That's it. So n is nothing but a total set of vertices, total number of routers. Okay, total number of routers in the entire subnetwork. Okay, total number of routers in the entire subnetwork. Okay, and n prime is nothing but a subset of router. Okay, n prime is nothing but a subset of routers in the least cost route. In the least cost path. For example, if you take this, now in this case, the least cost path may be u to x, x to y. Okay, let me take this is the least cost route. Okay, now n is nothing but u, v, w, x, y, z. N prime is nothing but u, x, y, z. Okay, so subset of routers in the least cost path is nothing but n prime. Okay, n is a total number of actual set of routers in the entire topology. So to find out the least cost route, you have to consider the entire routers, all the routers to be considered to find out n prime. Okay, so sometimes n prime may be equal to n, but that's a first case. Sometimes that may also happen. N prime is nothing but a set of routers in the least cost route to reach the destination. That's it. Okay, so these are the basic terminology. So with that, we will start our algorithm. Okay, I need a fresh new page, and this picture is also up there. Okay, let me take this, and the equivalent algorithm. What I'm going to do here is, this is based on our next shortest path algorithm. Okay, so in this particular algorithm we have two phases. One is the initialization phase. Okay, I'll type, I think that is better. The first phase is the initialization phase. Okay, so you have to do something for creating the topology. Okay, next phase is the iterative phase. Okay, so initialization phase will happen only once. Okay, so the next phase is the iterative phase that should be executed for every node in the network. Okay, so initialization phase, what is that? It's nothing but just to create actually I have shown a graph topology here. Okay, but in the real scenario, routers just acquires the information link state packet from each and every other router. That's it. Okay, this particular topology to be constructed by the router U. Okay, upon receiving the link state packet. Okay, so if for example, if there is no link state packet from Y, then there is no route to reach Y, and the cost to reach Y it's also be infinity. Okay, so initialization means you should initialize something. Okay, so let me initialize. The first one is n prime. Okay, n prime is equal to first initial router, the least cost route. Okay, definitely the source router is one of the router. Destination router is also another router. Here we need to find out the cost to reach is it. Okay, so the source router is U. Not only is it, we are going to construct a forwarding table. Forwarding table means it should have the entry for each and every other router. That means the least cost route to reach B, least cost route to reach X, least cost route to reach Y, and least cost route to reach Z. Okay, it should find out least cost route to reach each and every other router, because ultimately we need to construct the forwarding table. This is not for one transmission. This is for entire set of transmission. Okay, so the first one, in the least cost route, in the set of nodes, only one node is available, that is a source node. Okay, source node here is U. Okay, then we have to assign the cast. In this case, U knows its U knows the cast to reach its neighbor. Who are the neighbors? Its direct neighbors are U is directly attached with X, connected with X, directly connected with B, directly connected with W. So U knows the cast to reach X, B, and W alone. Okay, so for those casts to be assigned respectively, that is U to X cast to be 1, U to V cast to be 2, and U to W cast to be 5. Other routers Y and Z not yet known, not yet available with U, so that the cost to reach those router will be infinity initially. Okay, so let me do this for all nodes. Okay, for all nodes in N. Okay, entire set of nodes. Okay, for all nodes, we have the variable V. Each and every node in the list to be extracted. If check it out whether the V is a neighbor or not. Okay, if V is a neighbor, then you can attach the cast weight directly. Okay, if V is a neighboring node, then neighboring node of which node? U. Okay, if it is a neighboring node of U, then directly assign the cast D of V is equal to cast to reach V from U. So U comma V, a direct cast is available. Okay, else if the node is not a neighboring node, non-neighbor node, then D of V to be assigned with a value called infinity. Infinity. Okay, infinity. So this is what the initialization process. So initially, the router U knows its cast to reach its direct neighbors V, X, and W. For other neighbors, other routers, non-neighbors, the cast to reach those routers are assigned with the infinity value. Okay. Now let's move on to the iterative process. In this iterative process, the requirement is that this infinity value to be reassigned with actual values. Okay, so we need to find out the cost to reach non-neighboring node. Okay, we need to find out the cost to reach non-neighboring node. That is what our ultimate requirement. Okay, you have to explore from neighboring node. Okay, so what is the first step here? Find a node W such that that should not be in n prime already in the list. Okay, in addition to that, the cost of W, it should be the minimum. Okay, it should be minimum. Okay, cost of W, it should be minimum. Okay. I think better we can come here because I need this diagram later. Okay, so find out a node from the N1 list. Okay, find out the node from N list. Okay, and that should not be added in the least cost path. Okay, it should not be in the list N1, N prime. And in addition to that, that node should have the minimum cost from the current node. Okay, so if it is so, then add that node, add W to N prime. Okay, and then we have to update the neighboring nodes. Okay, so you have to update all the neighboring nodes of W, D of B. Okay, for each neighbor V, I have to NEI for each neighbor V of W. Okay, and you have to consider that should not be in the list also, n prime subset list. Okay, if it is so, just to find out or update the minimum cost, because sometimes the direct cost may be, if for example if you take this diagram, u to v u to w cost, direct link cost is 5. Okay, but if you consider this u to x, x to y, y to w, that cost is 3. 3 is smaller than 5, because ultimately we need least cost route only. Okay, so sometimes the direct link may be costly route as compared to the indirect link. Okay, so you have to update it. So we are going to update it based on the currently selected node. Okay, what we are going to do here is dw is equal to find out the minimum of already computed weight value d of v, comma the newly computed node d of w, neighboring node plus, because we have to consider the cost to reach that neighbor also, c of w comma v. Okay, so this formula is used to find out minimal cost link to reach each and every neighbor V of the currently selected node W. Okay, so that's it. So this process to be repeated. Okay, this is actually a least cost path. Okay, so this process to be repeated until, okay, actually you have to do this entire process to be repeated. Okay, this iterative process, this process to be repeated infinitely. So loop, okay, loop around this, select each and every unexplored node and find out the cost, okay, and update the cost. Okay, so until this loop to be repeated until n prime is equal to n, okay, because we need to find out the least cost path for each and every other router. Okay, until n1 is equal to n, you have to repeat this iterative process. Okay, so let's do this with this diagram. Okay, so let me perform this initialization process first and then iterative process. Okay, I will take it out the table. Okay, okay. So first step is the initialization step. Okay, I'm going to just draw the table here, steps, and initially what should be n prime, a subset of nodes for least cost route. Okay, and initially the zeroth step, only one node in the list. Okay, so only one node in the list, the source node. Okay, so source node is u. Then what I have to do, for all node B, the neighboring node cost to be assigned with its direct link cost, all other cost to be assigned with infinity. Okay, so I have to do that. For this, what are the other nodes? B, W, X, Y, Z. Okay, so let me take this is D of B, comma P of B. Okay, I will reduce this viewpoint so that I will give more space here. Okay, first neighbor D and then second neighbor W. So D of W to be computed and the previous node of W to be constructed. Similarly, D of X, comma P of X. Then we have two more nodes, D of Y, comma P of Y. Then finally we have Y then Z. Okay, D of Z, comma P of. P of Z. Okay, so this is the column. For initially, U knows its direct neighbors only. Okay, so use a direct neighbor U, X, and W. Okay, so for those the value can be fixed. Okay, so D of V, what is D of V? D of V, cost to reach V. Cost to reach V is, what is the cost to reach V from U? What is the cost to reach from to? What is its previous node? Because it's a direct neighbor, its previous node is nothing but U. And cost to reach W is 5 and its previous node is nothing but U. And cost to reach X is 1, its previous node is U. For others, it's unknown because non-neighboring node, so initially it will be infinity. Okay, so this is an initialization process. Now let's move on to the first step. Okay, so in this step we have to find out the W. Okay, what is this W? W which is not in the list, not in the subset. Okay, it should not be N1. Okay, you should not select U. And the minimum of DW. Okay, DW minimum. Okay, so the distance, minimal distance to be selected here. If you take this case, the minimal distance is nothing but 251. Minimum of 251 is nothing but 1. Okay, so now which node to be selected? The node X to be selected. Okay, node S to be added onto the list in the shortest route U, and then this is X. Okay, so from this X you have to update the table. Okay, I have just added this step over. I have added that selected minimal distance node to the N1 list. Okay, fine. Then I have to update its neighbors. Who are the neighbors to W? Neighbors to X? Who are the neighbors to X? Neighbors to X are B, B, Y, and U. Okay, but U already in the list, so that you will not be updated. But we have to update B and Y. Okay, this link should not be updated because U is already in the list. Okay, so X to Y and X to Y to be updated. Okay, so we have to update this X and Y. Okay, so let's see this, how this updation to be taken. So you cannot update this because it is already in the list. So 2 comma already in the least cost route. So 2 comma U. Now
X to W, ma'am.
X to yes, this one to be updated. Yes, fine. So X to W, this is 3. Okay, so already existing cost is 5. Okay, now this is the cost is 3. Okay, but see here, what we have to do here is you have to take it out that new link cost plus the cost to reach W also. Okay, so here what is W? X. What is the cost to reach X? Cost to reach X is 1 already. Now the cost to reach W is 1 plus 3. So you have to use the value. Here is you can achieve the least cost as 4. And the previous node. Now what is the previous node? Previous node is not U. Okay, we can reach W through X. Okay, so its previous node is nothing but a current node. Okay, X. Okay, so fine. So this is already minimum. X is also in the list, so that you cannot update this. Okay, so this will be same, you cannot update it. But Y not in the list, and it's also a neighbor, so you have to update it. Okay, Y is not in the list. Already the cost is infinity. Definitely the infinity is larger than any computed value. So the newly computed value is nothing but 1. Okay, that is cost of W comma V is 1, but cost to reach X is already 1. So this is nothing but 1 plus 1, 2. And its previous node is nothing but through X only you can reach this Y. Okay, but is it not a neighbor of X? Okay, so still the cost is unknown. Okay, so this is a result of the first iteration. Okay, so now the Z is not added onto the list, only 2 nodes are added, so that we have to get into the next iteration. Okay, so next iteration, in this you have to select the minimum. Okay, so 4, 1, comma 2. So what is the minimal? Sorry, 4, comma 2. 1 already in the list, 2 is also already in the list. Okay, so you have to select the minimum of 4, comma 2, comma infinity. Okay, so the selected now node is nothing but the node Y. Okay, so this node should not be selected because it is already in the list. X is also already in the list, so you have to find out the minimum of 4, comma 2, comma infinity. So the selector node is Y. Okay, so U, X, Y. Now the node is Y. Y to be explored. Who are? Yes, please.
Ma'am, the first one is DV or DU, ma'am?
Which one?
The column, ma'am.
V.
First one.
V.
Yes, ma'am. Now in the second step, both V and Y have 2, right, ma'am, cost. In the second iteration, both have cost 2, right, ma'am.
Yes, yes. Sorry. I'm sorry. Both has cost 2. You can select any one. Now I have selected X. Uh, I have selected Y instead of V. Okay, both has same cost. Either you can explore with this V, or otherwise you can explore with Y. Anyone.
Okay, ma'am.
Agree?
Yes, ma'am. Okay, ma'am.
Okay. So the minimum cost is 2, so Y is added onto the list. Now for Y, who are the neighbors? The neighbors are X is one neighbor, W is one neighbor, and Z. Okay, so I have to update X, W, and Z. Okay, so if you take U, X, Y, so this will be same. So there is no change in this. Take this 2 comma U, okay, because V is not a direct neighbor, so you need not update it. For W is a direct neighbor, okay, so already the cost to reach Y is 2, okay, already the cost to reach Y is 2. So now Y to W neighborhood cost is 1, so the newly estimated cost is 3, okay, so 3 is less than 4, so now I have to update it. Okay, so 3, new estimation is 3, and the previous node, so just the explode from Y, so the previous node is Y. Okay, and then this 1 comma U remains same, this is the least cost route, and 2 comma X just selected, that is the least cost route. From Y there is a direct link to Z. Now I have to update it. Infinity comma the cost to reach Y already 2, okay, so 2 plus 2, this link cost is 2, so 4, infinity comma 4, the minimum value is 4. Okay, so 4, which node to be used here? The previous node is nothing but Y. From Y I have explored, so that Y is used here. Okay, so similarly here we have computed some least cost route, but still this iteration to be continued until you include all the nodes in this list. Okay, now 3 nodes are in the list, 2 more node not yet added, so that you have to proceed further. Okay, so the next step U, X, Y. Okay, so now we have to find out, we have to select the least cost node. As you said, either you can start from V and then Y, but I have selected Y. Now I am going to select V now. Okay, V and U both are having same cost. Okay, so if you select V as next node, so 2 comma U remains same. There is no change in this. Okay, because for V, who are the neighbors? U is one neighbor, that is already in the list, that cannot be updated. W is one neighbor, okay, and X is another neighbor. Okay, so X is another neighbor, W is another neighbor. 2 neighbors to be updated. Okay, so this is 2 comma U, there is no updation, and 3 comma Y, cost is 3. You can reach Y with a cost 3, okay, and through V, okay, V to W cost is 3, okay, so V cost already 2, 2 plus 3 is 5, 5 is greater than 3, so that cannot be updated. Okay, new route cannot be used here. Similarly here, it is X, X through from V you can reach X, that is already the cost to reach V is 2, so 2 plus 2 is 4. Now existing cost is 1, so 1 less than 4, so that I can use 1 comma U. So 2 comma X, the cost remains same, because Y cost, if you take Y is not a neighboring, so you cannot update it. Okay, if you take Z, so Z you can reach Y. Okay, Y Z is not in the neighboring node, so that cannot be updated. So 4 comma Y. Okay, so still we have added only 4 nodes. Okay, totally we have 6 nodes, so 2 more nodes to be added, so that go for a next iteration. Okay, so the fourth iteration you have to select the minimal among this. Okay, so the minimum value here is U already in the list, X is already in the list, Y is already in the list, V, okay, and the remaining elements are only W and Z. Okay, if you take a W and Z, the minimal cost is W. So there U, X, Y, V, W to be added here. So from W, all the neighbors to be explored. From W, the neighbors are U, V, Y and Z. Okay, so from W to U, the cost is 5, but existing cost is smaller than this, 2 comma U. From the W node remains same. Okay, so now the X node, the cost to reach X, to reach W, the cost is 3. 3 plus 3 is 6. Okay, new estimated cost for X is 6, but existing cost is 1. So 1 is the minimum one. So and Y, cost to reach W is 3. 3 plus 1 is 4, but already having the value 2. So 2 is less than this, so it won't be updated. Then cost to reach Z is 3 plus 5. 7, but the existing cost is 4, so 7 is greater than 4, so no updation here. So 4 comma Y. Okay, so similarly we have to go for one more iteration because only one more node to be added. So the final element is U, X, Y, V, W. That only one node to be added, so you need not worry about any minimal cost. Z to be added. Okay, so from Z you have to explore all the neighbors. If you explore neighbor from Z, 4 and W is one neighbor, Y is one neighbor. So those nodes to be added. So V cannot be modified. To take W, to reach Z the cost is 4. 4 plus 5 is 9. So new estimation to reach W is 9, but existing estimation is 3. So that is better. So we can use this. Similarly, the X node 1 comma U, and for because X is not a direct neighbor, so you can use as it is. Okay, and then Y is from Z you can reach Y with the cost to 2. Already the cost to reach W Z is 4, so 4 plus 2 is 6. Okay, but existing value is 2, so 2 less than 6, so that you can take it out 2 comma X. So this one no updation, 4 comma Z. Okay, so this is simply our shortest path algorithm to complete this table. This table is not a forwarding table. Okay, so based on this table we have to construct the forwarding table for U. Okay, so this just we have applied this distance shortest path algorithm to complete this table. Okay, this table is not a forwarding table. Based on this table we are going to construct the forwarding table for U. Okay, the forwarding table for U should have the entry, only one entry to reach each and every other neighbor. Okay, so let me proceed with the forwarding table construction and the weakness, strength and weakness of link state routing, because this is highly dynamic routing. The most important problem with the link state routing is that the adaptive or the frequent change in the path. Okay, frequent oscillation in the path selection. Okay, that is also one problem with link state routing. So we'll continue the forwarding table construction based on this table, as well as the pros and cons of link state routing in the next class. Okay, just I'll stop here.